Just like that, we are at the end of the section. All right, just one more video and that will continue the whole section. So honestly, this video is really nothing new, just some applications, some extra examples for you if you want more math. Example 2. Find and classify. Ooh, I love hearing that word, classify. Local extrema. Ooh, I like that word too. That's 2 words that I like. So many words that I like. Find and classify the local extrema for y equals 1 minus x e to the 2x. Back to chapter 2. All right. We'll sprinkle in a little chapter 2 from time to time. Local extrema. We need to find critical points, remember? All right. So go back to chapter 2 and say find critical points. Critical points are when the derivative equals 0 or is undefined. But we never talk about undefined critical points in this class, but it's a thing. All right. So we need to find the derivative. How do I take the derivative of this? We are in need of our good friend, the product rule. Product rule says derivative of the first thing, derivative of 1 minus x is negative 1 times the second function, plus the first thing times the derivative of the second thing. Derivative of an exponential function is itself. Oh, but there's something up. We have to use the chain rule. Multiply by the derivative of the inside, which is just 2. So we have to take this derivative and set it equal to 0. Solve for x. Simplify a little bit. Negative e to the 2x plus 2, 1 minus x, e to the 2x. Couple of ways to proceed from here. We can combine like terms. We can factor. Factoring is going to be really nice. Anytime you're trying to solve an equation that equals 0, factoring is good. Principle of zero products. So if we factor out an e to the 2x, in the first term, we're just left with a negative 1. If we take out an e to the 2x here, all we're left with is negative 1. In the second one, we're left with a 2 times 1 minus x. So now the solutions of this equation are going to be when, if things are factored, when the first thing equals 0, or when the second thing equals 0. Let's distribute that 2 while we're at it, right? 2 times 1 is 2, minus 2 times x. Now this first thing will never happen. That's the word impossible. You can't see it because it's behind my head. The second thing, though, is certainly very possible. Add a 2x to both sides, we're going to get 1 equals 2x, or x equals 1/2. There's a critical point at this x coordinate, but we need to find the point and we need to classify it. Okay, critical points are points. Points have x coordinates and y coordinates. When x equals 1/2, what is the y coordinate? Well, we have a function. Let's use it. When x is equal to 1, what is our function? Our function is this. So let's plug in 1. Half. Plugging in 1 would actually be very silly. Let's plug in 1/2 because that's the x coordinate. All right, so we're going to get y is equal to, I already forgot the function, 1 minus x times e to the 2x. And that simplifies kind of nice. 1 minus 1/2 is just 1/2. 2 times 1/2 is just 1. Okay. We get e over 2, or 1/2 e. Type that into a calculator, and you should get 1.3591. So our critical point is when x is equal to 1/2 and y is equal to 1/2 e. Remember, critical points are our options for local extrema. Is this a local min? Is this a local max? Is it neither? We don't know. Okay? We can either use a second derivative test or the first derivative test, depending on what you prefer. To use the second derivative test, we have to go down here, look at our derivative, and take the derivative again. I don't really want to take the derivative again. Okay? So what I'm going to do, you could take the derivative again. It's actually not that bad. Let's use a first derivative test here. No, second derivative test. Let's do it. All right, so remember that y prime we found, you could use either. Y prime we found was this thing right here, which is e to the 2x times that leftovers. What did the leftovers simplify to, right? Oops, wrong direction. What did the leftovers simplify to? Well, we FOILed it out. And it simplified to just 1 minus 2x. Yeah, 1 minus 2x. Actually, the derivative is almost the exact same as the original function. So second derivative test means we need the second derivative. Take the derivative again. Derivative of the first function is 2e to the 2x multiplied by the second function, plus the original first function times the derivative of the second function, which is negative 2. And you could simplify this again, but all we really care about for the second derivative test is what is y prime at this x value. We're going to plug this in for x to use our second derivative test. So if we plug that in for x, what do we get? Right, when x is equals 1/2, our second derivative is equal to 2 times e to the 2 times 1/2 times 1 minus 2 times 1/2 plus e to the 2 times 1/2 times negative 2. We type that all into a calculator and let's see what we get. So we're going to get 2 times e times 1 minus 1. Oh, that whole first term is 0. Plus e times negative 2. We'll get negative 2e. But again, the value is not so important. What's important is the sign. Right? Specifically, right? At this point, when x is 1/2, our second derivative is negative. That's what matters. Second derivative is negative. First derivative is increasing or decreasing. Second derivative is concavity. So negative means concave down. It's the frowny face. If you've got a frowny face, is that a local max or a local min? It's a local max. All right. So by the second derivative test, we found out that this critical point up here is a local max. And there we go. And again, we're going to check our answers. The point 1/2, and remember 1/2 e is about 1.35. Is there a local max on this graph? Well, there's the graph. Ah, there is a local max. Where's that local max? It's right here. Ooh, 1/2 and 1.359. Great. There it is. You can see it in all of its glory that we indeed found and classified it. No problem. Pat yourself on the back. Let's do one more problem. Okay. So we have a painting was purchased 6 years ago for $100K, and it's valued at some function after T years. So the value, right, is changing every year. It's appreciating. It's getting more valuable over time. Some things get more valuable over time. Something gets less valuable over time. The question is, at what rate? So as soon as you see that rate, that's derivative. Rate is derivative. That's very important. At what rate will it be appreciating, which means going up, in 2020, given that that v of t, that appreciation function, is given like that? So we need to find the rate, because we're asked to find the rate. The rate is the derivative. We're going to find v prime of t, the derivative of all this. It's a constant times a function. If it were two functions, we'd have to use a product rule. Since it's only a constant times a function, we just bring that constant out in front. Multiply by the derivative of the function. The derivative of this exponential function right here, derivative of an exponential, is itself e to the t over 5. Multiply, chain rule, by the derivative of the inside. And remember, t over 5, that's the same as 1/5 t. The derivative is just going to be 1/5. So v prime of t is actually just 1/5 of 100k, just 20k, times e to the t over 5. So we found the derivative, we found the rate, but specifically it wanted to know at what rate it'll be appreciating in 2020. And you don't plug in 2020 for t. You plug in 2020 for t, you're going to find out this is the purchase of their lives, and it's going to be such a big number. 2020, right? That's t equals 5, right? 5 years after 2015. Just like how 2021 feels like 5 years after 2020. That was the worst joke I've made in class in a long time. So we plug in 5. All right, that's going to be 20,000 times e to the 5 over 5. Plug that into a calculator, and you're going to get approximately some number. 20,000 times e to the 1, $54,365.64 approximately. So when they purchased it, it was worth 100K. Every year it's getting more and more valuable. And specifically, in 2020, after 2020, it's going to be worth about an extra $54,000. Every year it grows. That's about how much it's going to grow in 2020. So technically dollars per year. These are units. Yeah. Like so. Yeah, this painting is really a hot ticket item. Anyway, that should be the entire section. You should be ready to go. Be very careful. There is some problems like this. Remember that velocity. Oh, this is terrible to write this now. If I have a position function, this is completely unrelated to the problem above. But if I have a position function, remember the derivative of that position function is the velocity. It has nothing to do with this v up here. And remember that the derivative of velocity is acceleration. You'll have to use that a little bit in this section, homework. Have a good one.